Yeah, hi, we are the spatial indexing team, and we are going to talk about our module which does spatial indexing for our in memory database. We started off with utilizing PR quadry for points and MXCF quadry for rectangles. In this video, we are going to demonstrate how the code is structured and how a user can access our component. So the main file, as you can see, is the spatial index IMPL, which is open here. And the functions that the user can actually execute is the search on both the point and the rectangle collection, as well as create index functions for both. And we have update as well as delete functions for these points as well as rectangle collections as well. So once a user has created an index, they can access it through the spatial index IMPL to perform search as well as delete operations. And what we have done for the user is, since we have integrated our code in CLion, user can actually utilize the cmake list.txt file that we have to create their own custom make file, or they can run this code in CLion to generate an exe, which we have done. The exe in our case is named as advdb test, and our advdb test executable is available here, which the user can execute on the command line and run it with we will be reading the csv file from one of the folders for our test, which is the bulk load test. And Akhil will be talking about the how the tests and are run and the results are captured.
Hi. So yeah, this is our PR quad node code. So currently we have made changes to make our leaf capacity code to be leaf capacity size to be called from the PR quad tree. So we can configure the current size, and we kind of performed a test case analysis to see how the leaf capacity changes and how the size changes with respect to the data size. If you clearly remember, last time I talked about the point collection size. That is the current algorithm that is provided by Professor Anand Samit from University of Maryland discusses that we split the quad node, the root quad node or any quad node to four quad nodes after you say insert 2 points. So you can consider that you have a collection size of say 2 points and then you have to split it. So what we have done is we have made that configurable, so if you can make the collection sizes 4, 8, 16, and then split it into the required quad nodes. So, and that is what the leaf capacity here mentions, because here based on the leaf capacity, if you look at our code here, here if point size is less than leaf capacity, we keep inserting into this particular collection, and once it increases the size, we do a subdivide logic. That subdivide is the logic that you make the quad node and then insert into the respective quad node's children. So we've this is the current code change, and more important than the code change, we have done a study regarding that. And if you look at PR quad tree, you can provide the date the leaf capacity here. So you give the leaf capacity here and do that. So we've written a bulk load script which bulk loads all the CSV data. This is the point.csv that is provided by Professor Sawat in his DDS class, and which has been provided to us by the integration team. We have bulk loaded the script. The total size of the data of this script is say 2.7 MB, and we have tested this for multiple versions of leaf capacity. If you look at it here, we have generated or make files with respect to different leaf capacities. So what I have done is I've changed the leaf capacity from 4.1.2.4.8.16 to 2048 and generated the required make files. And now we're going to run this. This is the top command that's already running. If you notice, there is no current advdb test process running. So now I'll be running the shell script which runs all of this. Okay. So now if you look at it, okay, and this is stop, right? So if you notice, this is the complete process list, and if you have a look at it, look at advdb1. You have 106 MB memory, then you have 2 with 61 MB, then 39, 28, 22, 20, and then if you have a look at it, for the current data set that we've been given, we are achieving a sweet spot of data size around at advdb 32, right? So yeah, you can, yeah, we are achieving a really good sweet spot at size advdb 32. and the reason could be is that the data is saturating a number of subdivide logics. So this essentially proves that even with one, if even with one divide, uh, yeah, and we've you know uh, run this data on Excel sheet and plotted the required graph. So if you see the graph, we plotted until 128, and if you notice, at leaf capacity 1, that is at Professor Anand Samat's logic of subdividing after say 2, and our modification logic of subdividing say after 2, 4, 8, actually reduces the total memory size that's being held by the quad tree. So at 1 you have 106 MB, at 2 you have 61 MB. So even with just a degree, with just increasing leaf capacity by 2, you're seeing a complete reduction of space. So you can say take 8 or 16 or 32 and then reduce the space significantly for the in-memory index. And this is the current analysis we have done for this week, to see if what algorithm change we have made is actually significant and it actually helps the in-memory index, and this actually proves that it does. Thank you.